we can probably do it. I've never successfully done it. I haven't tried setting up a Hall effect apparatus in years, but I was cleaning out my garage the other day and found I have a nice long piece of aluminum, which should work perfect for this. It's thick enough and long enough and wide enough where it should work perfect. So I'm going to bring it to school. I'm going to try and set it up and see if it'll work. If it works, great. If not, I'll tell you about my spectacular fail. But we'll give it a try. Um, the Hall effect is an interesting concept, but what's great about it is that it can prove what the charge carriers are inside a wire, and that's why we study the Hall effect. So let me first draw what we're going to have to need. We need a kind of a thick piece of metal. So I need to have something that's hollow on the inside looking. So border's good, fill there, and that. So there we go. I want you to imagine that I have a wire and that the wire is attached to a thick piece of conducting metal. Yep.
Did you say the Hall effect can determine what type of charge are in a wire?
It can tell us what the charge carriers are inside the wire. So there we go. We had to pick a direction for the current. So let's assume the current's traveling this way. If we assume that in this apparatus, the particles that are passing through here are positive charged particles, if we assume that, then, hold on just a minute, I need to do something real quick. Then, when the particles make it to the piece of metal, we would say that they would have some velocity this direction, and we'll call that the drift velocity. Remember, inside a piece of metal, the charge carriers are moving. The speed at which they're moving depends on a number of factors. How many charge carriers there are, the density of the material, stuff like that. But there's a drift velocity that all the particles in the wire are experiencing. If I then take this piece of metal and surround it with a magnetic field, and I'm choosing a magnetic field that is into the board, then there will exist a force on this positive charged particle. In this case, the force would be in what direction? Up or down? Just hoping we all get it right. It's a positive particle, so, right? The velocity is this way. Magnetic field into the board, so I'm thinking the force will be up. So the particle will experience a magnetic force upwards. Now, in this piece of metal, these particles would be able then to drift in the direction of the unbalanced force. So as the positive particles enter the metal, they would begin to move towards the top of the metal because they're experiencing an unbalanced force. So the particles would begin to move along the top here. We would get an excess amount of positive charge here. That would also draw particles from their normal uniform distribution in the wire, making an area down here that would be slightly negatively charged because of the loss of the general flow of positive particles that would have been down there. Suggesting then that there would be a potential difference between the top and bottom of this wire. At the same time, that would begin to generate an electric field this way. So the particles would drift towards the top, but as they accumulated at the top for their trip across the wire, we would get a stronger and stronger electric field inside the space between these two, or I'm sorry, inside the width of this wire. And eventually, an electric force would develop so where new particles coming into the wire would experience a balanced force. So we'd reach a steady state condition. So I first flip this on, the particles begin to move, and I'd have an ever increasing potential difference due to this ever increasing electric field that would eventually taper off and reach a steady state condition. This is known as the Hall voltage. And the Hall voltage is something that can be measured. So all you need to have is a uniform magnetic field, a wide piece of wire, and the flow of charged particles, a current. Now, here's the thing. We assumed that the particles that were passing into the wire, or passing through the wire due to the current, were positively charged. And it created a positive side and a negative side like this. What if they were negatively charged? Remember, if the current is to the right, that means if they're negatively charged particles, the negative particles would be traveling to the left. Right? Because we're saying that the current is to the right, but we know negative charges go in the opposite direction of conventional current. Let's surround the wire with the same magnetic field we had before. There will be a force on these negatively charged particles as they enter the wire. Velocity's this way, magnetic field's that way, so the force must be upwards, right? They're negative particles. So the force on them will be in the opposite direction than we would expect for a positive particle. We're expecting that, therefore, to be upwards. So they are also pushed upwards due to the action of the magnetic force. But of course, what that means, though, is that the negative charges will begin to accumulate at the top. Not the positive charges, the negative charges will accumulate at the top, which would mean that we would get a surplus of positive charges available at the bottom. And although it is likely we would reach the same steady state condition that we had before, same size potential difference, you realize what the issue is, right? Under this circumstances, the top part becomes negative and the bottom part becomes positive. The voltage would be inverted if the charge carriers were negative and not positive. The Hall effect is, although you can measure the Hall voltage, sure, what the Hall effect actually tells us is what is actually moving through the wire and in what direction. It clarifies that our charge carrying particle was actually the negative particle, and our precepts about conventional current were wrong. The Hall effect is a fantastically simple experiment, and it is somewhat amazing that it took until the end of the 18th century for people to kind of figure this out. And I don't know much about the Hall effect. The reason we know the current's going that way is because this flow of charge could only happen if my battery were connected with the anode on one side and the cathode on the other. So we know the direction of the current. A negative particle wouldn't go from the negative side of the battery to the positive side of the battery. I'm sorry, it wouldn't go from the positive side of the battery to the negative side of the battery. A negative particle would have to go from the negative side of the battery to the positive side. So if this is the positive side of the battery and this is the negative side of the battery, you couldn't get an electron to go that way. So I think that's how they knew what the direction of the current was. Interesting, a little bit. I like the Hall effect. It's kind of interesting. I've yet to be able to create the Hall effect in my classroom. I measured it in college once, but the apparatus was so convoluted. By the time I was done setting it up, I couldn't tell what was what. And wires everywhere. And it was mostly because we had to measure something else in addition to the Hall effect when I was in college. I couldn't tell you what that is now, but I just remember it being a kind of a mess. But I have, like I said, I have a piece of metal that might work. We'll try it. I've got a whole stack of these neodymium magnets in the back that should be super powerful, and I know I can get them all arranged in the right direction to generate a relatively uniform magnetic field. The only problem with them is they're of such high magnetic field that they scare me a little bit. I'm afraid I'm gonna pinch my fingers off when I'm setting them up. I have tried to do. I have a hard time. It's hard to set up good magnetic field experiments because it's hard to generate a good magnetic field that will work for a lot of the experiments. You know, we can set up motors and stuff. That's not hard, but some of these are. So what I'd like to do for these last few minutes is I want to turn our attention. The concept of the Hall effect should bring up something in your mind. And if it hasn't yet, let me direct you. There's particles moving in the wire. And because there's particles moving in the wire, when you apply a magnetic field to a current carrying wire, all of those particles can be affected at the same moment. If the Hall effect is any indication that the particles can move inside the wire, what happens to the wire if instead of you make it nice and wide, you make it very narrow? Meaning, let's say I have a wire and I connect it up in space. And I fill that space with a magnetic field. I don't know why I favor magnetic fields that go into the board. It takes a lot longer to draw them than a bunch of dots, but I almost always go with that first. I think it's because it's easier to just put my finger downwards into the page. If I establish a current in the wire in this direction, then that suggests that there will be a bunch of positive particles or negative particles. Take your pick. Do you want to do this from the standpoint of positive charge flow or negative charge flow? It's best if we do this from the standpoint of positive charge flow because we know the convention still exists. What we're about to talk about here predates the Hall effect. These are not free particles. These particles are forced to travel in the wire. So they can't move freely in the space. When you turn the current on in an area that has a magnetic field, each one of these positively charged particles will experience its own independent force. By the way, what direction would that force be? Could you point in the direction that that force would be? It would be that way. Because the wire constrains the motion of the particles, all of the particles experience a force of the same magnitude and in the same direction. They can't escape the wire. So instead, the entire wire experiences a force. Current isn't a vector, but the direction of the length of the wire is. So under this circumstance, you can push a wire one way or the other. Now, this might not feel like that's a big deal, but remember, the current in a wire can be controlled by a switch. I can turn on and off the current at the push of a button, which means I can force something to move at the push of a button.
Is that L?
L, length of wire. Now we're going to pick this back up on Monday, but what this is the first opportunity to convert electrical energy into direct mechanical energy, which is what we'll talk about on Monday. What's that? It would be to the left. Oh, I was looking at the board and not looking at my paper. So clearly, even me, I get confused between the board and the paper. And I'm just writing these arrows for Andrew's benefit because he's not here today. There. That would be direction.